Greetings. Lamport's signature scheme is conceptually simple, and it's relatively straightforward to assess its security against both classical and quantum attacks. Nonetheless, it has significant limitations, including large public keys, large private keys, and large signatures, as well as the fact that its private key can be used to sign only one message. In this video, I'll present solutions that address these limitations. I'll quickly review the Lamport one-time signature scheme that I presented in the previous video. The scheme relies on a pre-image resistant hash function G and a collision resistant hash function H. To generate a key pair, Alice first selects n pairs of random n-bit strings denoted Xij. She then computes their G hashes Yij. Alice's private key is a list of Xij values, and her public key is the list of Yij values. To sign a message M, Alice hashes it to obtain little h, whose bits are denoted H0, H1 up to Hn-1. For each bit Hj, she reveals either X0j if Hj equals 0, or X1j if Hj equals 1. Her signature is composed of these disclosed values. Signature verification requires hashing M and checking that each signature component Sj hashes via G to the corresponding public key component indexed by Hj and J. The first problem with Lamport is the large size of private keys. Lamport private keys and public keys are each 2 n² bits long, and the signature is n² bits. For n equals 256, this translates to 16,384 bytes for keys and 8,192 bytes for signatures. These are far larger than those in RSA and elliptic curve signature schemes. To reduce the private key size, the private key components Xij are generated from a randomly selected secret n-bit seed and a counter, for example, by using a pseudorandom function prf. The prf could be HMAC, with the seed serving as a secret key. The seed is securely stored and used to generate the Xij when needed. For n equals 256, the private key is reduced to 256 bits, or just 32 bytes. The second drawback is the large size of public keys and signatures. The large sizes stem from signing the bits of the message hash 1 bit at a time. To address this, Winternits proposed signing the bits of the message hash 1 W-bit block at a time using the notion of hash chains. Simply put, a hash chain is created by repeatedly applying a pre-image resistant hash function to a randomly chosen initial value. Let G be a pre-image resistant function, and let X0 be a randomly chosen n-bit string. Define a sequence of n-bit strings as follows. X0 is the starting value. For each I at least 1, Xi is computed by applying G to the previous term Xi minus 1. Such a sequence X0, X1 up to Xm is called a hash chain of length m. Given any term Xi in the chain, anyone can efficiently compute all later terms. This is because G is an efficiently computable and public function. However, it's infeasible to compute any earlier term since G is pre-image resistant. For example, if someone knows X3, then they can easily compute X4, X5, and so on. But finding X2, X1, or X0 from X3 is infeasible. Here's a toy example of the Winternits OTS that will illustrate the main ideas. Let G be a pre-image resistant hash function, and let H be a 12-bit hash function. The small size of H's hash values is what makes this a toy example. You should imagine that H is a 256-bit hash function and is collision resistant. The Winternits parameter is set to W equals 2. To generate a key pair, Alice first selects a random n-bit string x0 and applies G to x0 3 times in succession. She does this 3 times because 2 to the power W minus 1 is 3. So she forms this hash chain of length 3 starting at x0. She repeats this process to get a total of 6 such hash chains. There are 6 chains because this is the number of 2-bit blocks in a hash value for the hash function H. Alice's private key consists of the list of 6 starting values x0, x1 up to x5. Her public key is a list of 6 final hash values y0, y1 up to y5. Now, suppose that Alice wishes to sign a message M. She hashes M to get the 12-bit hash value H, which she divides into 6 2-bit blocks denoted H0, H1 up to H5. Suppose that these values, interpreted as integers, are 2, 3, 0, 2, 1, and 0. The first block of H is 2, so Alice sets the first component of her signature to the third element of the first hash chain. Similarly, since the second block of H is 3, Alice sets the second component of her signature to the fourth element of the second hash chain. She repeats this for each of the 2-bit blocks in H. Alice's signature on M is S0, S1 up to S5. To verify Alice's signed message, Bob hashes M to reproduce H, and then checks that the signature components SI are correct. So applying G to SI the remaining number of times until the chain ends should result in the public key component YI. For example, Bob verifies the first signature component as 0 by hashing it once and confirming that the resulting value is equal to Y0. Similarly, he checks the second signature component S1 by checking that it is equal to Y1, and so on. The security of the Winternits one-time signature scheme relies on keeping most hash chain elements secret. If an adversary only knows Alice's public key Y, represented by the green dots, they can only forge signatures for messages whose hash value is a string of all ones. This is because the adversary cannot compute any elements on the hash chains above the YIs. Now, suppose that an adversary obtains one signed message. The signature reveals about half the elements in each hash chain on average. These are the blue dots in the figure and all dots beneath them. Additional signed messages will reveal more and more of each hash chain. Thus, Alice should only use her private key to sign one message. However, there is a more serious security concern. Once an attacker obtains one signed message, they can easily compute the signature for all messages M* whose hash values H* has individual 2-bit blocks HI* that are each at least as large as the corresponding block HI for the message M. This is because the attacker can compute all subsequent elements in each hash chain beyond the revealed elements, in other words, the blue dots. To address this security concern, hash chains are added for a certain checksum of the message hash. The checksum of the message hash H is defined to be the sum of the terms 2 to the W minus 1 minus HI for each block HI of H. This is the distance between the signature component SI and the public key component YI. In the toy example shown, where W equals 2, the first term of the sum is 2 to the w minus 1 minus h0, which is 1 since h0 is 2. Note that 1 is the distance between the signature component S0 and Y0. Similarly, the second term of the sum is 2 squared minus 1 minus h1, which is 0 since h1 is 3. Note that 0 is the distance between the signature component S1 and Y1. Since each term of the checksum is at most 2 to the w minus 1, or 3 in the example, the checksum of h is at most 6 times 3, which is 18. Such a checksum can be represented as a binary string of length at most 5, which can be written as a sequence of 3 2-bit blocks, after prepending a 0-bit. So Alice uses 3 additional hash chains to represent the 2-bit blocks of the message hash's checksum. In the example shown, the checksum of h is 10. You can check this, which is written as a length 6 binary string 001010. Alice's signature on M will include the elements on the checksum hash chains corresponding to the 2-bit blocks in the checksum. So, since the first block of the checksum is 0, she includes x6 in the signature. Since the second block of the checksum is 2, she includes the third element in the corresponding hash chain in the signature. And since the third block of the checksum is 2, she includes the third element in the corresponding hash chain in the signature. So the signed message now reveals the 9 blue dots in the figure.
We'll now explain how the introduction of hash chains for the checksum of the message hash prevents the potential attack mentioned on the previous slide. In this attack, an adversary who obtains a single signed message can potentially forge signatures on new messages.
Suppose now that an adversary has seen the signature on this message M and wishes to forge Alice's signature on the message M star. Since the forger cannot move up a hash chain, they can only succeed if each block HI star of the hash of M star is at least equal to HI. Also, since H is collision resistant, for real-world parameters not n equals 12, we can assume that H star, the hash of M star, is not equal to H, the hash of M, because otherwise the forger has found a collision for H. Thus, there is at least one index I for which HI star is strictly greater than HI. But then the checksum of H star is strictly less than the checksum of H. Hence, at least one of the 2-bit blocks of the checksum of H star is strictly less than the corresponding 2-bit block of the checksum of H. Consequently, because the forger cannot move up a hash chain, they will be unable to compute the signature component for this checksum block. For example, suppose that the third block H8 star of the last 2-bit block of the checksum of H star is 01. Then, the last signature component of M star should be G of X8. However, the forger cannot compute this from S8.
This argument shows that the Winternits OTS is a secure one-time signature scheme, assuming that H is collision resistant and G is pre-image resistant. In the next slide, we'll provide a complete description of the Winternits one-time signature scheme.
G is pre-image resistant and H is collision resistant. Parameters include the Winternits parameter W, which is a divisor of n, L1, which is a number of W-bit blocks in a hash value H, L2, which is a number of W-bit blocks in the checksum, and L, the sum of L1 and L2. To generate a key pair, Alice selects L random n-bit strings xi and computes hash chains of length 2 to the w minus 1 starting at the xi's. The final values of the hash chains are denoted by yi. Alice's private key is a list of starting values, and her public key is a list of final values. To sign the message M, Alice computes its hash H and the checksum of H. The hash H and checksum are split into W-bit blocks. Alice's signature on M consists of L components, where the ith component Si is the element on the ith hash chain that is Hi apart from the starting value Xi. To verify Alice's signed message, Bob recomputes the hash H of M and its checksum, and verifies that the signature components Si are correct. So Bob applies G to each Si the remaining number of times until the chain ends, which is 2 to the W minus 1 minus Hi times. And he checks that the resulting value is equal to the public key component Yi. Let's compare Lamport and Winternit's public key and signature sizes. We'll take n to be 256 for both schemes and select Winternit's parameter W equals 8. So hash chains have length 255. The Winternit's length parameters are L1 equals 32, L2 equals 2, and L equals 34. A Winternit's public key consists of 34 strings Xi, each 32 bytes long, for a total of 1088 bytes. This is significantly smaller than the Lamport public key, which is 16,384 bytes long. Similarly, a Winternit signature is 1,088 bytes long, smaller than Lamport's 8,192 byte signatures. Note that a Winternit's private key can be generated from a 256-bit secret seed and a counter. So a private key is only 32 bytes long. Both Lamport's and Winternit's one-time signature scheme share the limitation that a private key can securely sign only one message. This is impractical for most applications due to the significant overhead of securely distributing public verification keys, for example, through certificates. A straightforward solution is to generate many OTS key pairs and use them one at a time. The drawback with the solution is that if one expects to sign many messages, then one would have to generate a large number of OTS key pairs. Thus, the total size of all the OTS public keys will be very large. Ideally, a public key should be small, and the corresponding private key should be small and permitted to securely sign many messages. An elegant solution to this problem is to use a Merkle tree to authenticate the OTS public keys. A Merkle tree is a complete binary tree whose leaves represent the hashes of the individual OTS public keys. Each internal node's value is obtained by hashing the concatenation of the values of its two children, recursively building up to a single root hash. This root hash serves as a user's long-term public key. Authentication paths to the root can be used to efficiently confirm the authenticity of an individual OTS public key, as we'll see next. Here is an example of a Merkle tree for authenticating 8 Winternit's public keys. The tree has height 3. An n-bit collision-resistant hash function f is used. The tree has 8 leaves, which are assigned the hash values of the corresponding Winternit's public keys. The parent of the 2 leftmost leaves is assigned the hash of H0 and H1. The parent of the next 2 leftmost leaves is assigned the hash of H2 and H3. And so on. This process continues recursively until reaching the root node. The root value R serves as Alice's long-term public key. We'll assume that this long-term public key is securely distributed to Bob, perhaps by including it in a certificate. Alice signs messages sequentially using the private keys corresponding to Y0, Y1, Y2, and so on in that order. For each signature, she must include the corresponding OTS public key. For example, she must include Y2 with the third message she signs. Alice must also include additional data that allows Bob to authenticate the public key. Suppose that Alice has signed her third message, so she includes Y2 with her signature. She constructs a unique path from the leaf node H2 to the root of the tree. This path is from H2 to H9, H9 to H12, and H12 to R. Alice's signature includes the hash values assigned to the sibling nodes of all nodes in this path. So along with Y2, her signature includes H3, which is a sibling of H2, and H8, the sibling of H9, and H13, the sibling of H12. The receiver Bob, who we're assuming has an authentic copy of R, can verify the authenticity of Y2 as follows. Bob first hashes Y2 to obtain H2. He then hashes H2 and H3 to obtain H9, hashes H8 and H9 to obtain H12, and hashes H12 and H13 to obtain a candidate root R primed. If R prime equals R, then Bob concludes that Y2 is authentic. Security relies on the collision resistance of the hash function f. Suppose that an adversary wishes to substitute Alice's public key Y2 with the public key Y2 primed of their choosing. The hash H2 primed of Y2 primed will likely be different from H2, otherwise the adversary has found a collision for H, which we're assuming is infeasible to do. Since H2 changes, so must H9, otherwise the adversary has found a collision for F. Similarly, since H9 changes, so must H12. And since H12 changes, so must R. Thus, thanks to the collision resistance of F, the adversary is unable to replace Y2 with the public key of its choosing. Let's determine the size of public keys, private keys, and signatures when the Winternits OTS is used with parameters n equals 256, w equals 8, and L equals 34. We'll use a Merkle tree of height 20, which implies there are 2 to the 20 leaves, so approximately 1 million Winternits OTS key pairs. The long-term public key consists of a single hash value, so it's 256 bits or 32 bytes long. The private key is also 32 bytes long, since the individual Winternits private keys for all 1 million key pairs can be generated when needed from a 256-bit secret seed and suitable counters. Recall that a Winternit signature itself is 1088 bytes long. The additional data included in the signature is the OTS public key YI, which is another 1088 bytes, and 20 hash values for the authentication path from HI to the root. Since each hash value is 32 bytes long, the total signature size is 2816 bytes.
Thus, the Merkle tree results in a very small long-term public key, substantially increased functionality, allowing 1 million signatures without changing the long-term public key, and only a modest increase in signature size, from 1088 bytes to 2816 bytes.
The fourth problem we'll address is the following. If one wishes to sign up to 2 to the D messages without changing one's long-term public key, the Merkle tree must have height D. However, a major drawback is that key generation is very slow, since all 2 to the D OTS key pairs need to be generated in advance in order to compute the root R of the Merkle tree. To address this inefficiency, the Merkle tree is divided into smaller trees to form a hypertree, also called a multitree. Here is a Merkle tree of height d equals 4, which we'll divide into a 2-layer hypertree. The first layer is composed of a single Merkle tree of height 2, and the second layer consists of 4 Merkle trees, each also of height 2. Of course, hypertrees can have more than 2 layers. The leaves of the layer 1 Merkle tree are associated with OTS key pairs. Their private keys for these pairs are used to sign the roots of the layer 2 Merkle trees. Meanwhile, the leaves of the layer 2 Merkle trees are associated with OTS key pairs, each of whose private keys are used to sign one message. If the layer 1 tree has height d1 and the layer 2 trees each have height d2, then the total number of messages that can be signed is 2 to the power d1 plus d2. The main benefit of using hypertrees is that only the layer 1 Merkle tree needs to be built during key generation to determine the long-term public key, which is the root of the layer 1 Merkle tree. This significantly speeds up key generation. The layer 2 trees can be constructed on demand when signatures are required. For instance, when signing her first message, Alice would generate the first layer 2 Merkle tree. She signs the root of this tree using the private key associated with the leftmost leaf of the layer 1 tree. And she signs the actual message using the private key associated with the leftmost leaf of the layer 2 tree. Her signature will include the layer 1 signature, which authenticates the layer 2 root, the layer 2 authentication path, and the layer 1 authentication path. A verifier can use these values to confirm the authenticity of the OTS public keys involved. Alice repeats this process for signing the second, third, and fourth messages. The fifth message triggers the creation of the second layer 2 Merkle tree. The Winternits OTS keys are used sequentially, with layer 2 Merkle trees built as needed. One drawback of using hypertrees is that signatures are slightly longer and verification a bit slower, because the signature is now comprised of 2 OTS signatures instead of 1. On the positive side, hypertrees enable distributed signing. Different cryptographic modules can independently generate and manage their own layer 2 trees. This reduces the risk of key reuse, while allowing multiple modules to share signing authority.
The Leighton-Micali signature scheme, LMS, employs the Winternits OTS with Merkle trees and some additional optimizations to enhance security. LMS will be presented in video V5. See you there!